Hello, and welcome back. This week we're going to encounter two new operations on vectors. Both of these involve taking two vectors, so let's say vector u and vector v, and combining them in such a way that we produce a new object. So we had this with addition. This was similar for vector addition, but what came out was a vector that represented the sum of those two other vectors. The dot product, which we're talking about in this series of videos, will take two vectors and produce a scalar. Maybe something, I don't know, like C. Let me actually just write what it is. U dot V. Dot product, and that represents a scalar. So taking two vectors, producing just a number from these. And question is, what does that represent? So we'll get to the definition in a second. We'll also see another operation this week called the cross product, which will take two vectors and produce another vector. But we'll start with just this, the dot product. Now, the motivation behind the dot product comes from an example in physics, and that's sort of the best way to start any discussion of the dot product is to connect it to that physics idea. And the idea is of work. So what is work? Maybe you've encountered this before, but work is if we have a constant force, so imagine there's a big block, something like this, and you apply a constant force to that parallel to the ground, and the block moves around along the ground. If you take the force and multiply it by the distance that it's traveled, so a constant force acting in the direction of motion, and you multiply those two quantities, you obtain a value, a quantity that is measured in terms of energy, and that's the work that it took to move that object that distance. So this is the idea of work. Now, as I mentioned, when the force is acting in the direction of motion, and when it's constant, so a constant force in the direction of motion, it's really easy to compute what the work is. We just take however much force multiplied by however much distance was traveled. So not too bad. However, the big question is, how do we calculate work if the force vector, as we know, force is actually a vector. It has a direction and a magnitude, not just a magnitude like we have here. And same with displacement, which is really what we're interested in, is how does that object move? We can draw a vector from whose tail is where the box started and whose head is where the box ended up. And that gives us the displacement vector. So we really have these two vectors that we're working with, and we'd like to take these two. So we have force vector, we have displacement vector, and we want to combine these two to give us a scalar quantity. Energy is just a scalar, which is the work done. So this is a scalar that comes from two vectors. All right, well, let's take a look at a few examples here to just clarify what I mean and actually calculate this. How do I actually calculate it when the force is not in the direction of motion? So again, we start up here. So I'm not super imaginative here. We're just taking a block, we're applying a force to it, and it's moving along this vector d. This is representing its displacement. So over on the right-hand side, this is where the block ended up. Left-hand side is where we started. This force is being constant throughout the movement of the block. In this case, the work done is, as I said before, just force times distance. But force and displacement, these are vectors. So what we're really talking about here in this sort of one-dimensional case is the magnitude of the force, how much force, times how much displacement. That's the magnitude of the displacement, whatever this length is. So in this case, that works. This formula works. It's super easy and nice, and we like it. However, things aren't so nice in the real world. It's not always just a force in the direction of motion. Instead, we might have a force acting not quite in the direction of motion. So how do we compute work here? Well, the idea is we want to get it to this first figure here. So I'm going to do some steps here. What I want to do is I want to decompose. So I want to decompose F into two vectors, one parallel to D. That'll be the part of the force that is in the direction of motion. and one perpendicular to D. And that's sort of the wasted part of the force. So we haven't exactly talked about decomposing vectors yet, but we can talk about that here. So I take my displacement, I take my force, I can measure some angle between these. That's not too hard of a task. We can find some angle theta between the force and the displacement. And then what I can do is I can write this force. If you notice, go back to vector addition, I can think of this force rather as a sum of two other vectors, one in the direction of motion. So maybe one would call this, say, Fx, something like this, the force in the direction of the x direction like this, and then one perpendicular to that because I need them to add together to give me F. And so something like this. Notice how if I go from the tail of Fx to the head, I'll call this one Fy, to the head of Fy, I get the vector F. And so that gives us our decomposition that I mentioned we were after. So this is Fx plus Fy. And that gives us F. And now we have, so this Fy, this isn't going to do anything. This isn't going to add any work to the situation. This isn't contributing at all. This is completely perpendicular to the direction of motion. So Fy doesn't contribute any work. However, Fx is exactly in the direction of motion. And so what that tells me then is work should be not F, but rather Fx, the one that's in the direction of the displacement, the magnitude of that, again, times the amount of displacement. So if we can get a hold of what Fx is, we can find the magnitude of that and get D. So what is Fx? And really I just need its magnitude. Well, that comes from the angle here. Go back to trigonometry. Cosine of this angle times the length of the force vector F gives me the length of the force vector Fx. So that is magnitude of Fx is magnitude of F, arrows, times cosine of theta. Replacing that over here, I have that work is, I just need to take the magnitude of F times cosine theta times magnitude of the displacement. Or as we'll normally write it with our magnitudes together, F times the distance times cosine of theta. So that's pretty cool. And in fact, this is our dot product. This is what we're going to call our dot product. This is work. And just to add another example here, it doesn't matter if our force is opposing the direction of motion. In this case, since I'm working against the direction of motion, we should consider the work negative. I'm taking energy out of that system. And so, again, we could decompose F into these two subvectors. And again, now cosine of theta, sorry, that's not my cosine of theta. My theta now looks like this. It's bigger. In this case, theta is greater than pi over 2. Here it was less than pi over 2, or 90 degrees. And cosine of that will be negative. Now this works out really nicely because I know that the work should end up being negative since I'm opposing the motion. So again, this vector here has magnitude F cosine theta, and again, work is F d cosine theta, where theta is the angle between them. Now you might ask, what if theta is bigger than pi? So right here, pi is greater than theta. What if what if the angle is bigger than pi? What if my force vector is like down here like this? Turns out we don't have to actually worry about that situation, because if I just perform a rotation on this, or maybe a reflection, I can always get it to the situation where theta is between 0 and pi. So we assume the angle between the vectors theta, no matter which situation I'm in, it's safe to assume it's between 0 and less than or equal to pi. It could actually be 0 or pi. Again, if it's not, we can just sort of rotate the whole picture and end up with a situation like this. Okay, so this is work, and this motivates what the dot product is. We want just an operation that takes two vectors and produces this quantity, which represents the work done. And that's exactly what the dot product is. We define the dot product. This is our definition as this: uv cosine theta, where theta is the angle between them, between 0 and pi. Now, a little caveat here, this angle is not defined if one of my vectors is 0, right? We can't define an angle between those two because one of them has no direction, or both. In this case, we just say the dot product is 0 and that the angle between them is undefined. So that covers this sort of weird case if, say, our force is 0 or if we don't move the object at all. And so that is the dot product. Work is F dot D, but we can extend, we can abstract beyond work and just define this for any two vectors. And the question is, well, what does that tell us for any two vectors? What is this quantity that represents work in some situations? What does it mean in other situations? That's what we're getting to. How can we use it for other purposes? And what does it mean theoretically? These are all really good questions that we're going to answer. So one last slide here as just an example. Compute the dot product of these two vectors. Two situations here. So one, u is 2i minus 6j. I already have my axes set up like this, so I'm going to let u be red and v be blue. So let's see. 2i minus 6j. Remember, this is the same as if it's 2i minus 6j, this is 2 in the x direction and minus 6 in the y direction. But we use both of these forms sort of interchangeably, so it's important to get used to this. Oops, careful, I'm in 3 dimensions, so I need a third component to this. There's no k's here. Remember, I, j, and k represented x, y, and z respectively, those unit coordinate vectors. V here is just 12k, so this would be 0, 0, 12, if you like this representation more. And it's always good to go back and forth between these in case we didn't quite get it the first time. So here, 12k, my vector v is just pointing straight up like this. So we could imagine, if you want, we can imagine v as the displacement. Why not? It doesn't have to be, but for our purposes, we can imagine as displacement. So this object that's at the origin moved 12 units upward. And the force that's applied, u, is 2 minus 6j. So that would be 2 minus 6j. That's over here. And that's in the xy plane. So I'm applying this force to this object that's moving up. Maybe it's an elevator or something that's moving up, and I'm sort of, I don't know, in the elevator shaft, pushing on the elevator in this direction, but the elevator's not moving in that direction at all. It's just moving up, so I'm not contributing any energy to this, the movement of the object. I'm not doing, my force is not contributing to any work being done. This is V, by the way, and this is U. And so in this case, my force is completely perpendicular to the direction of motion, and so, or alternatively, we can measure the angle between these two, theta, which should be 90 degrees, or pi. So theta equals pi over 2, or 0 degrees, pi over 2 radians, or 0 degrees. In either case, cosine of theta then is 0, and so the work done, I don't care about the magnitude of u, magnitude of v, I don't even have to compute those. I know off the bat, because this angle, because the two vectors are perpendicular to each other, that I end up with 0, because cosine theta is 0. And that was a factor, u dot v. So that's an important thing to remember. Two perpendicular vectors, their dot product will be 0. We'll talk a little bit more about that later on. Over in this situation, again, I'll let u be red and v be blue. U is square root of 3, 1. That's about over here. By the way, I didn't label these. This is my x, this is my y, and this is our normal setup, x, y, z. Sometimes I forget that, but if it looks like this, this is the setup. And then v is 0, 1. So now these things are not perpendicular to each other. So that means I got a little bit of work to do. I need to compute the work done. I gotta do work to compute work. This is u v cosine theta. So I'm going to need the magnitude of u, the magnitude of v, and I'm going to need the angle between them. So we have some work to do. What is the angle between these two? This is square root of 3 in the x direction, and then 1 up like this. And then here, this is 1 up and square root of 3 in this direction. I have some triangles here. In particular, I have a right triangle with u and v here. And so theta is the inverse tangent of the opposite over the adjacent side. So theta then is the inverse tangent, tan inverse, of square root of 3 over 1. And take a second, you can either pull out your calculator or remember the unit circle. I would get an angle of square root of 3 over 1 by doing sine over cosine. Square root of 3 over 2 divided by a half would get this. So sine, that would correspond to 60 degrees, or pi over 3 radians. So that is my angle here. Hence, now I can do this. Well, what's my magnitude of u? What's my magnitude of v? Good to refresh our memory of how to compute magnitudes. This is square root of square root of 3 squared plus 1 squared. That's 3 plus 1, that's 4. Square root of 4 is 2. Magnitude of u is 2. V is a unit vector, right? It's 0, 1. This is j, right? This is the same as j in 2 dimensions. That's a unit vector. That's just 1. So magnitude u times magnitude v, that's 2. Cosine theta, or rather theta is 60, so cosine of theta is a half. Right? Remember that unit circle. We're going to be using it a lot, just like in every other calculus class. So that's 2 times a half. The work done here is, let me just write it out, 2 times a half is exactly 1. Now notice I'm not putting units on any of these things. We're not in a physics class, so I'm not super concerned with that at the moment. I just want the quantity that comes from the dot product, right? Well, yeah, I guess I'm saying work here. But really, I'm not necessarily calculating. We can think of it like work, but generally what I'm doing is calculating the dot product of 2 vectors. Remember, work and dot product are really the same thing, or rather, work is a specific instance of the dot product. And so we get just 1. Okay, so that's our introduction to the dot product. There's a lot of stuff going on here with the dot product, more to see. In the next video, we talk about this apparent difficulty given 2 vectors producing an angle between them. If I just take 2 vectors in 3 space here, it's not in general an easy problem to find the angle between them. This could take a little bit of work if I just have 2 sort of arbitrary vectors. I don't really know which direction they're pointing to be able to measure this angle between them. Not always so easy. So we'd like a better way to do that. In particular, we'd like a better way to compute the dot product. Is there an easier way to compute the dot product? That's the subject of the next video. I will see you there.